Good day everyone and welcome to our last lesson. This is lesson 10, gas mixtures with one condensable component. So let's begin. Before we start, we need to take a short review of the gas laws because gas laws here would be very important because remember we will be dealing mainly with gases. I have listed here four of the most commonly used gas laws. Boyle's law. This is PV or pressure times volume is equal to constant. You might recognize this as P1 V1 is equal to P2 times V2, essentially saying that pressure is inversely proportional to volume. Next is Charles' law. Volume is directly proportional to temperature, or V over T is equal to constant, or that's V1 over T1 is equal to V2 over T2. Next is the combined gas law. This is just the combination of Boyle's law and Charles' law. That's PV over T is equal to constant, or P1 V1 over T1 is equal to P2 V2 over T2. And lastly, the most commonly used, the ideal gas law wherein PV over NT is equal to constant. The constant in this case is the real gas constant R. So that becomes PV equals nRT. Okay, let's proceed. Let's review Dalton's law of partial pressure. So I think you have already tackled this in your general chemistry, but just to be safe, I will be giving a review of Dalton's law. Now, Dalton's law of partial pressures only applies to ideal gases in mixtures. If you are dealing with real gases, Dalton's law might not apply. Okay? And it is a prerequisite that, of course, first and foremost, the gas that you are dealing with should be a mixture before you apply Dalton's law of partial pressures because it should only apply to mixtures. The main statement is, it states that the total pressure of a mixture of gases is the sum of the individual partial pressures. So this is like saying the total number of moles is simply the sum of the individual moles of the components. So you are simply replacing moles with pressure, and then you have Dalton's law of partial pressures. I have here an example. For a gas mixture containing 1 atmosphere of A and 1 atmosphere of B, we can say that the total pressure is simply equal to PA plus PB. If both are 1 atmosphere, then the total pressure is 2 atmosphere. Now, the interesting part is we can actually draw an equivalency between the mole fraction and the so-called pressure fractions. If we review the definition of a mole fraction, I will be using the small letter y to denote mole fractions in this case because we want to use the x variable as the mole fraction for liquid substances, while we want to use y for gaseous substances or for vapors. No, so that's just a little disambiguation in this lesson. So whenever you see y, you always think that it's a mole fraction of a gas, and if it's x, it's the mole fraction of a liquid. So in this case, the mole fraction of A in the gas phase is equal to the number of moles of A over the total number of moles. So this is no surprise to you. You already know this. It's just the definition of mole fraction. But we can actually equate that to the pressure fraction such that the mole fraction of A is equal to the partial pressure of A divided by the total pressure. So in this case, if the partial pressure of A is 1 atmosphere and the total pressure is 2 atmospheres, we can say that the mole fraction of A is 0.5, which should make sense because A and B are present in equal amounts. Now, if I rearrange this equation, mole fraction of A is equal to partial pressure of A over total pressure, we reach this main equation of Dalton's law. The partial pressure of A is equal to the mole fraction of A multiplied by the total pressure. So later on in our problem solving, you will be using this equation a lot. Okay, so don't forget this. This gives us an equivalency between mole fraction in gases and pressure fractions in gases. Let's proceed. Now, this is our main topic in this last lesson. No? We want to define, or we want to stress the importance of air and water mixtures. Now, air and water mixtures are very important in the industry because there's so many processes that rely on air and water mixtures. Here are some examples: drying, During our past lesson, when I first introduced drying to you, I mentioned that there are two types of drying. There's the direct heating drying, wherein a heating element is used to dry the substance. And then there's another type of drying wherein hot air is used to remove moisture from the substance. That is where the air and water mixture for drying enters. Okay, so I think we will be answering an example regarding this later. Next, you have humidification and dehumidification. You might be seeing this in your homes already. If you have a humidifier in your house wherein you are placing essential oils and then the machine puffs up some smoke, no? So that's an example of a humidifier, and the process is humidification. The opposite, dehumidification, it's just a fancy term for saying that you are removing moisture from the air. Humidification is the process of adding moisture to the air. Dehumidification is the process of removing moisture from the air. One of the most common examples of a dehumidifier that you have already encountered but you might not have noticed, no, is your air conditioning unit, aircon. If you take a look at the back end of the aircon, there's water dripping there at the back, no. That water actually comes from the room that's being kept cold by the air conditioning unit, no? So it's a dehumidifier. The aircon is a dehumidifier in the sense that it takes water vapor from the room that it's trying to cool and it condenses it and it releases it outside as liquid water. Okay? So again, humidifiers, air and water mixture calculations are important, as you will see later. Next, we have evaporation and condensation. Next, we have vapor liquid absorption. We have already tackled absorption, no, but we did not recognize the possibility of water vaporizing, no, because that's a real possibility. And the air and water mixture is a very important topic because it's an example of a gaseous system that's very commonly available or that's very commonly encountered with one condensable component. So let's dwell on this. Condensable components. So what makes a substance condensable? When we are talking of gases, we actually have two classes. You have here your condensable and the non-condensable. So how do you determine if a gas is condensable or if it is non-condensable? If you can condense that substance from the gas phase to the liquid phase at ambient temperatures, meaning at temperatures above 0 degrees Celsius or sometimes even a little bit below 0 degrees Celsius, that is a condensable substance. What are classic example of condensable substances? Water. You can easily condense water vapor from the air, no? You can actually see this when you are when you go out early in the morning and then you see dew on the grass. So that dew on the grass is condensed water from the air, no? Clouds are actually a condensed phase of water. Water is the most commonly encountered condensable component. How about non-condensable components? I will be listing here air. Now, air is oxygen and nitrogen. Technically, oxygen and nitrogen can be turned to a liquid. You have already heard of it, no? Liquid nitrogen. But when we are saying non-condensable in this context, we are saying that we cannot condense it at ambient conditions. So at room temperature or even at 0 degrees Celsius, we cannot condense nitrogen except by adding very, very high amounts of pressure, which is impractical. Okay? So that's what separates condensable from non-condensable gases. Can you condense it relatively easy at room conditions? No? So at atmospheric pressure, at room temperature. So water fits the title of a condensable component. Other notable condensable components, you have benzene, you have ethanol, no, or ethyl alcohol. You can easily evaporate ethyl alcohol, but you can also easily condense it, and so on and so forth. The most common non-condensable substances are oxygen, nitrogen, You have hydrogen, helium, argon, and so on and so forth. Now, we must set up a terminology that easily differentiates condensable from non-condensable gases. This is where the term vapor comes in. Now, all your life, I think you are using the term vapor wrong. Previously, no, we are free to use the terms vapor and gas interchangeably. You can say water vapor, you can say water in the state of a gas, or you can say gaseous water, no, and etc. etc. But for this instance, for the sake of clarity, all condensable components will be referred to as vapor. So we say water vapor, ethanol vapor, benzene vapor, to signify that those substances are in the gaseous state. We just refer to them as vapor because they are condensable. Okay? While the non-condensable components, these are the gases that you can call as true gas. You can call them as gaseous. Okay? So we use gas or gaseous for non-condensable components, gaseous nitrogen, gaseous oxygen, while we call the condensable components as vapor, water vapor, benzene vapor. Okay? Always remember this. Okay, next, we have Raoult's law. So Raoult's law is a very important law alongside Dalton's law because in almost every problem, you will be using either one of those equations or even both. No? So what is Raoult's law? Under ideal behavior, we assume that the partial pressure of a component in a gaseous mixture is equal to its vapor pressure at a specified temperature. What does this equation mean? So take a look at this equation. I have mentioned to you earlier that we will be differentiating between mole fraction in the liquid and in the gas phase. No? So this X sub A is the mole fraction of substance A in the liquid phase, and this Y sub A is the mole fraction of substance A in the vapor phase or in the gas phase. This P sub A with the asterisk, we call this the vapor pressure. Okay, we will be discussing the vapor pressure in the next slide. P sub T here is the total pressure. So let me first illustrate a scenario to you. Let's have a scenario wherein you have a glass of water. A glass of water with a little bit of liquid water at the bottom. This liquid water exerts a vapor pressure. Okay? And the vapor pressure right above the level of the water, we call this the vapor pressure of water. Okay? How do we then equate the vapor pressure of water, so this vapor pressure, how do we then equate the vapor pressure of water to the partial pressure of water in the vapor phase? You know that if this is an open glass, right above the water you have air. So this air, you have nitrogen and oxygen, but it's not just pure air. You also have here water vapor. That's why we call it air and water mixtures, right? The question now is, what is the partial pressure of water in this case? Is the partial pressure of water equivalent to the vapor pressure? We use Raoult's law. So again, Raoult's law is the mole fraction of water in the liquid phase multiplied by the vapor pressure of water. Now, the vapor pressure of water is constant at a certain temperature, okay? Is equal to the mole fraction of water in the vapor phase multiplied by the total pressure. Now, if my liquid phase is pure water, that means that my X H2O is equal to 1. This is for pure liquid phase. If X is equal to 1, then that drastically simplifies our equation. This becomes the vapor pressure of water is equal to the mole fraction of water in the vapor phase multiplied by the total pressure. Does this equation look familiar? Remember, this was derived from Raoult's law. We have a similar equation. We say that the partial pressure of water is equal to the mole fraction of water in the vapor phase multiplied by the total pressure. What's this? This is Dalton's law. They're very similar. What's the difference? The main difference is here. In Dalton's law, we are talking about partial pressures. In Raoult's law, we are talking about vapor pressures. You might be asking, is Dalton's law equivalent to Raoult's law? Not always. But in this case, if it's under the condition of equilibrium, again, if it's under the condition of equilibrium, you can equate Dalton's law with Raoult's law because they have the same YH2O times P sub T. What we have is the partial pressure of water is equal to the vapor pressure of water. This is a very important equivalency that we will be using for majority of our computations. Now, to go back to my question earlier, is the vapor pressure of water in my glass equal to the partial pressure of water in the vapor phase? The answer is it depends. If it's at equilibrium, then yes, it's equal. If it's not at equilibrium, then it's not equal. Okay? One way of reminding yourself about the difference between partial pressure and vapor pressure is that vapor pressure is the maximum partial pressure. So the partial pressure can be less than the vapor pressure. They can be equal, but the partial pressure can never be greater than the vapor pressure at any given temperature and total pressure. Okay? Hold on to this equilibrium equivalency. We will go back to this later. And then I will also be teaching you how to spot conditions of equilibrium because not all processes come into equilibrium. Okay, let's go back. Okay, remember the difference between vapor pressure and partial pressure. To refresh you, the partial pressure, if you divide this to total pressure, is equivalent to mole fraction. That is always true. But the vapor pressure, we have a different definition. This is how we define vapor pressure. So vapor pressure is defined as the pressure exerted by the vapor immediately adjacent to the surface of a liquid, just like how I illustrated it to our water example earlier. The vapor pressure of a substance can be determined from a P versus T phase diagram. So I'm sure in general chemistry, you have encountered these types of diagrams, no? The pressure versus temperature diagram gives you this curve coming from the triple point up to the critical point of the substance. We call that the liquid vapor boundary line. Now, the liquid vapor boundary line, if you take any temperature, so let me illustrate this. Let me write the important equations. So this is Dalton's law. This is Raoult's law. Okay? If we go back to the pressure temperature phase diagram, this is the pressure temperature phase diagram for water. This is the critical point. This is the triple point. This is the solid phase. This is the liquid phase. And this is the vapor phase. Now, where can you find the vapor pressure in this graph? You can only find the vapor pressure as readings from this line, from the vapor liquid boundary line. How do we do that? If you have a copy of the phase diagram of the substance, what you can do is you can simply read the graph. For a certain temperature, let's say for example, this is 25 degrees Celsius, you simply project this up to the diagram and then project it to the P. The value of P here is the vapor pressure of the substance. Example, no, for water, at 25 degrees Celsius, the vapor pressure of water is 23.8 millimeters of mercury. So if you get a phase diagram of water, if you locate 25 degrees Celsius and then locate exactly where the two lines intersect, you see that the vapor pressure would read 23.8 millimeters of mercury. Okay? You can do this for any point of this graph. Any point of the graph. As long as you stay on the vapor liquid line. because the vapor liquid line will always give you the vapor pressure. Okay? Now, what if we don't have a copy of the graph? Because in the exam, you will not have a copy of the graph, and it's very cumbersome for us to be reading out of a graph. And sometimes we will not get the exact same readings, right? Because we read differently. Now, we have other options. We can model, or some people have modeled, this liquid vapor boundary line through the Clausius-Clapeyron equation. Now, you might be already familiar with the Clausius-Clapeyron equation from general chemistry, no? But it's not of this form. The Clausius-Clapeyron equation that you are familiar is the one with the ln P2 over P1. So let's write it. So I think one of the first introductions to you of the Clausius-Clapeyron equation goes like ln of P2 over P1 is equal to negative delta H vaporization over R times 1 over T1 minus 1 over T2. No? This is one of your first introductions to the Clausius-Clapeyron equation. Well, you can still use this. No? What you need here are two sets of values of pressure and temperature. So if you have, let's say for example, if you know the substance, let's say for example water, you can easily find for a value of the enthalpy of vaporization of water at atmospheric pressure. So what you need now, since R is a constant, you simply need a reference temperature or T1 and a reference pressure P1. You know the second temperature and you are solving for the new vapor pressure. Remember, the pressures here are vapor pressure if we are talking of the Clausius-Clapeyron equation. Okay? So I think we have an example later that will make use of the Clausius-Clapeyron equation. So we will just go back to this equation. But I will teach you the easiest way on how to determine the vapor pressure of a substance. The easiest way and the most practical way is through the Antoine equation. The Antoine equation is a model of the liquid vapor boundary line in the pressure temperature phase diagram. This is the general form of the formula. Logarithm, this is base 10. So logarithm of the vapor pressure is equal to the constants A minus B all over C plus T. The vapor pressure here is in millimeters of mercury. The temperature here is in degrees Celsius. And for water, at this temperature interval from 0 to 100 degrees Celsius, we have the values of A, B, and C. So what you're going to do is you simply substitute A, B, and C to this equation. If you're asked what is the vapor pressure of water at a certain temperature, you simply substitute the temperature, solve the equation, and you find the vapor pressure P. Okay? So this is applicable for almost all substances because the Antoine constants for majority of the relevant substances are already given. You can find Antoine equation constants in thermodynamic books or in our textbook. I think we also have in our textbook, no? Himmelblau or Felder. Expect that we will be heavily using this equation, okay? Because this is one of our easiest ways of determining vapor pressure. Okay, let's do an example so that you can absorb the equations and the concepts. Air and liquid water are contained at equilibrium in a closed chamber at 75 degrees Celsius and normal atmospheric pressure. Calculate the molar composition of the gas phase. So let me draw the given. We are given a closed container with water in it, liquid water. No? So if you take a look at the question, air and liquid water. So it does not matter how much liquid or how much air is in your vessel. The important thing is there is liquid water and then there is air. Now, it's said that the temperature of the system is 75 degrees Celsius. And the total pressure of the system is at 1 atmosphere. Now, there are some other keywords that will be important for us. No, when I was discussing Raoult's law, I mentioned to you about the term equilibrium. In this problem, it was explicitly stated that it is in equilibrium. And what do we know if the system is at equilibrium? We know that the partial pressure of water, because your condensable substance here is water vapor, the partial pressure is equal to the vapor pressure because of the condition of equilibrium. Now, in majority of the problems, they will not state if it's at equilibrium. So later on, we will have to devise guidelines on when to deduce if it is at equilibrium or not. Okay? But for now, since it was explicitly stated that it is at equilibrium, we can make use of Raoult's law and Dalton's law combined. Okay, and we are asked to find out the molar composition of the air, or the molar composition of the gas phase. Now first, you ask yourselves, what are the components in my gas phase? Or how many components do I have in my gas phase? You have air, and even though air is actually composed of many gas species, for engineering calculations, we are assuming that air is composed of nitrogen gas and oxygen gas. But is there something else in your air? There is. There is water vapor. In our past calculations, we are neglecting the amount of vapor pressure in our calculations in air, especially in our combustion calculations wherein there is air input. No, we are neglecting the air there. But after this lesson, you can no longer neglect the water vapor in the air. Okay. So we have three components of the gas phase. You have nitrogen, oxygen, and water vapor. The question is, how do we determine the composition of this gas phase? You're only given 75 degrees Celsius and 1 atmosphere. You're not even given the amount of water. So how do we do it? Let's first start with the equilibrium condition. In our equilibrium condition, we say that the partial pressure of water is equal to the vapor pressure of water. Do we have an equation to determine the vapor pressure of water? We have. That's the Antoine equation. So let me write the Antoine equation. Log of P is equal to A minus B over C plus T. We know that our temperature is 75 degrees Celsius. If we substitute A, B, and C, we can solve for P. So let's go back first to the Antoine equation. And then let's solve. So I will be inputting logarithmic of x. You can use shift solve, or if let's not use shift solve. How can you solve this equation when you don't have shift solve? You simply raise both sides of the equation by 10. So we have P is equal to 10 raised to A minus B over C plus T. And then we can get the vapor pressure. This is vapor pressure of water in millimeters of mercury. So let's try to substitute 10 raised to A is 8.07131 minus B is 1730.63 over C 233.426 plus T plus 75 equals. This is our answer. 288 millimeters mercury. Okay, So if it's 288 millimeters mercury, if that's your vapor pressure, based on the condition of equilibrium, this must also be your partial pressure. So we now know the partial pressure of water. To get the molar compositions, we simply have to get the mole fractions, and then we can simply multiply it by a given number of moles to get the molar composition. What's next? You go back to Dalton's law of partial pressures. What is Dalton's law of partial pressures? The partial pressure of water is equal to the mole fraction of water multiplied by the total pressure. Do we know the partial pressure of water? We do, because that came from the vapor pressure of water, and those are equal because of equilibrium. And we also know the total pressure of the system, that's 1 atmosphere. Therefore, we can already get the mole fraction of water. The mole fraction of water is 288 millimeters of mercury divided by atmospheric pressure, 760 millimeters of mercury. What do we have? 0.380. Now I have the mole fraction of the condensable component. How do I get the mole fractions of nitrogen and oxygen? Well, it's simple. The mole fraction of the condensable component plus the mole fraction of the non-condensable component is equal to 1. So, to get the mole fraction of air, we simply subtract this from 1. 0.62. And then, you know that air is 79% nitrogen and 21% oxygen. So therefore, you can get the mole fraction of nitrogen and oxygen. You simply multiply 0.62 times 0.79. That's 0.490. And then for oxygen, 0.62 times 0.21. 0.13. And if you add, that's 0.13 plus 0.49 plus 0.38, 100%. So we have determined the molar composition of the gas phase. You see, we did not even have to know how much water was inside the vessel. We also don't need to know how much air was present in the vessel. All we need to know is that our equilibrium condition was met. And then from that, we use Dalton's law to determine the composition of the gas phase. Okay? Always remember the equilibrium condition, and always remember the proper use of the Antoine equation. Okay. Next. Dew point. What is the dew point? So from the name itself, dew, that means that that's the temperature at which the condensable component starts to condense, or that is the minimum temperature at which your condensable component would start condensing. Okay? When you wake up in the morning and go out to a field of grass and then you see that there's dew, you then immediately know that the temperature of the air is lower than or equal to the dew point temperature of the air because you have condensed water. Okay? For our previous example, the problem explicitly stated that the vapor phase and the liquid phase are in equilibrium of each other. When we are talking of the dew point itself is an equilibrium condition. Whenever you read something that is at the dew point, that means that the partial pressure of the condensable component is equal to its vapor pressure. Automatic. At the dew point temperature only. Okay? If you go lower than the dew point temperature, you are still at the equilibrium condition. So the partial pressure is still equal to the vapor pressure. But if you're higher, if your actual temperature is still higher than the dew point temperature, you are not yet at equilibrium. Okay? So you can only apply the equilibrium condition at the dew point itself or at a temperature lower than the dew point temperature. Okay, let's try to solve examples. Okay. A stream of air at 100 degrees Celsius and 6.92 atmosphere contains 10% water by volume. Okay, so we have several questions. Let's write the given. I'm going to draw this with a unit. We have the feed, we have the product. Okay, so your stream of air, I will relegate that to the feed. So you have here air at a temperature of 100 degrees Celsius and at a total pressure of 6.92 atmospheres. This contains 10% water by volume. Now, you need to know this, no? The percent by volume is the same as percent by mole. So when they say it's percent by volume, you can already assume that it's also percent by mole. So this is 10% by mole water. The remaining 90% by mole here would be our air, in which 79% is the nitrogen, 21% is the oxygen. Okay, first question. What is the dew point of this sample of air? We are still looking at the feed itself. So your feed is 100 degrees Celsius, 6.92 atmosphere. What is its dew point temperature? So how do you get the dew point temperature? You again go to the equilibrium condition. Our equilibrium condition is the vapor pressure of water is equal to the partial pressure of water. That is what happens at the dew point temperature, right? So at a certain temperature, which is the dew point temperature, the vapor pressure is equal to the partial pressure. Now, what can we get here? Can we get the partial pressure or can we get the vapor pressure? The answer is you can immediately get the partial pressure. How do we get the partial pressure? Dalton's law. The mole fraction of water is equal to the partial pressure of water all over the total pressure. Rearranging, the partial pressure of water is equal to the mole fraction of water multiplied by the total pressure. Do we have the total pressure? Yes, that's 6.92 atmosphere. Do we have the mole fraction of water? Yes, that's 0.1 from 10% water by volume. So you can immediately solve for the partial pressure of water. That is 0.1 times 6.92. The partial pressure of water is 0.692 atmospheres. Now, because we are talking of the dew point, you know that that is an equilibrium condition. So this partial pressure is also equal to the vapor pressure of water at the dew point temperature. So how do you turn the partial pressure to a temperature? We go back to the Antoine equation. Remember, the Antoine equation is ln of P, and remember that this P is the vapor pressure of water is equal to A minus B over C plus T. What happens to this temperature term in the Antoine equation? This becomes the dew point temperature. This is your marker. If you are using vapor pressure in this place, then the temperature here becomes the dew point temperature. Okay, let's continue. So I now know the vapor pressure of water. I can substitute that to the Antoine equation and then we can get the dew point temperature. So solving this Antoine equation, you can use shift solve. So that's ln, it's not ln, it should be log. So you have to be careful on the form of your Antoine equation because some forms of Antoine equation uses natural logarithm instead of log. Or sometimes they use different units of pressure and temperature. Okay? So if that happens, the constants will be different. Okay, so let's follow this log. So logarithm of 0.692 equals A 8.07131. By the way, you don't have to memorize Antoine equation constants, no? You will always have access to those constants, even when you are in your other major subjects. You don't have to memorize Antoine equation constants. 1730.63, because there's so many constants. You have 3 constants per compound, and then there's hundreds and hundreds of compounds that utilize the Antoine equation. 233.426 plus dew point temperature is our x. And then solve. Sorry. We forgot to convert your pressure to millimeters of mercury. So our vapor pressure, 0.692, should be in millimeters mercury. Okay, so that is 0.692 times 760. Our dew point temperature is 90 degrees Celsius. Okay, how do we interpret this? Our interpretation is, if your gas stream or if your feed is cooled down to 90 degrees Celsius, your water vapor will start condensing. If you only reach 95 degrees Celsius, water will not condense. If you reach 91 degrees Celsius, water will not condense. It will only start condensing at 90 degrees Celsius. If you lower the temperature further to 80 degrees Celsius, water will still condense. Okay? So water will condense starting from the dew point temperature up to the lower temperatures. The answer to the first question is the dew point temperature of the air is 90 degrees Celsius. Okay? Next question. Calculate the percentage of the vapor that calculate the percentage of the vapor that condenses and the final composition of the gas phase if the air is cooled to 80 degrees Celsius at constant pressure. So we go back to our diagram. Now, we now know that our unit is a cooler because it says in the problem that we are cooling the gas to bring down the temperature to 80 degrees Celsius. So the temperature in your product is now 80 degrees Celsius, and it said it's at constant pressure, so the pressure is still 6.92 atmosphere. Now, the question is, how much water is now in your product? We are to determine the percentage of the vapor that condenses. So since this is a cooler, you're cooling the gas, and since the temperature of your product is below the dew point temperature of your feed, that means that there's something that condenses. And if there's something that condenses, you have to add a stream in your unit. You have to add the liquid water condensate. So we specified that the water here is liquid. So why do we have to separate the liquid water condensate from the gaseous product? Well, that's because they are of different phases. The stream W is liquid, stream P is still gaseous. Now, question, what are the components of my stream P, of my product? Or was I able to condense all of the water? The answer is no, because even if you lower the temperature of the gas to 0 degrees Celsius, there would still be water vapor in the air. So the safe answer here is you still have water vapor here, and you still have the air. Okay? The question is, how much water condenses? So this is where our material balance will come in. If you perform an OMB, this is simply F is equal to W plus P. Okay? Basic. If you perform the air balance, what do you get? You get the air in F is equal to the air in P. Meaning to say, air is a tie component, or air here is an inert. Whatever air enters in the feed, it also exits in P. Okay? The only thing that changes between the feed and the product is the water. If you perform the water balance, the water in F is equal to the water in W plus the water in P. We are required to determine the water in W. We already know how much water is in F because we know that your feed is 10% water. So this would just be as easy as selecting your basis as the amount of F. Let's say, for example, 100 moles of F. And then you already know how much water is in there. Okay? But the problem is you don't know how much water is left in the product because we need that to determine how much water was condensed. Okay? Now, a few things. I told you earlier that our equilibrium condition is the partial pressure of water is equal to the vapor pressure of water. So this is worth repeating to you over and over again so that you do not forget. Okay? And we get our equilibrium condition whenever we are at the dew point temperature or lower. Your product is at 80 degrees Celsius. That is lower than the dew point temperature of the feed, which is 90 degrees Celsius, which means that your product is at equilibrium. And since your product is at equilibrium, we can apply the equilibrium condition at the product. The partial pressure of water in the product is equal to the vapor pressure of water in the product. Okay? Now, the vapor pressure of water in the product, you can easily determine because you have the temperature of the product, 80 degrees Celsius, and you have the Antoine equation. Log P vapor is equal to A minus B over C plus T. You already know T. This is your 80 degrees Celsius. You can easily solve for the vapor pressure in the product. Okay, let's do that. Let's use shift solve again. So that's logarithm of P. We're solving for the vapor pressure. Is equal to A is 8.07131 minus B 1730.63 over C 233.426 plus X. Plus 80. So our unknown is the pressure. Okay. Our vapor pressure is 354.83. Vapor pressure of water, this is all at the product side, is equal to 354.53 millimeters mercury. Now, what do we get if we have the vapor pressure? Since your product is determined to be at equilibrium, it's not stated in the problem that it's at equilibrium, but we determined it because of the temperature being below the dew point temperature. This is now equal to the partial pressure of water in the product, and with that you can use Dalton's law. So how do we use Dalton's law? The mole fraction of water is simply the partial pressure of water over the total pressure. The partial pressure of water being equal to the vapor pressure, 354.53, over total pressure, 6.92 atmospheres multiplied by 760 to convert it to millimeters mercury. What is our mole fraction of water? 354.53, 6.92 times 760. 0.0674. That is the mole fraction of water in the product side. Now, can we solve the problem with this mole fraction? Yes, because we only need to set our basis for the feed, 100 moles of feed And then we can perform the water balance. We have the water in F is 0.1 times 100 is equal to W, because remember, W is pure water, it's pure liquid water, plus 0.0674 times P. And then your OMB is equal to 100, your OMB is 100 is equal to W plus P. And we can solve those two equations. So that's 1.0674.1 times 100. Second equation, 100. Your W is 3.50. And your product is 96.50. This is moles. So we have solved the problem. We have determined that we can condense 3.5 moles of water if you bring down the temperature from 100 degrees Celsius in the feed to 80 degrees Celsius in the product. Okay, let me go back here first. Another surefire equilibrium condition, whenever you see this in our problems, whenever you see condensate in this problem, this is a condensate. Whenever you see a condensate that was in contact with the product stream that is gaseous, so in this case, the product stream, which is the water condensate, was in contact with the gaseous product because the condensate came from the gaseous product, right? So they were in contact. You can say that this is already an equilibrium condition. Okay? Whenever you have a condensate that is an equilibrium condition, you can already equate the partial pressure to the vapor pressure in the product side. You only apply that in the product side. Okay, so we now have three known equilibrium conditions. The first is if the problem explicitly states that it's at equilibrium. Second, if you are at the dew point temperature or lower than the dew point temperature. And the third is if you have a condensate. Those are your equilibrium conditions so far. Okay, let's answer this last one. Calculate the percentage of the vapor that condenses and the final composition of the gas phase if the air is compressed to 11.18 atmospheres isothermally. By the way, in the second problem, we forgot to determine the final composition of the gas phase, but we already actually did solve for the mole fraction of water. So we now have that. You simply subtract this from 1, you get the mole fraction of air. Okay? So we kind of answered it already. So let me first erase some things. For the last question, calculate the percentage of the vapor that condenses and the final composition of the gas phase if the air is compressed to 11.18 atmospheres isothermally. Isothermal meaning constant temperature. So therefore, the temperature in your product is still 100 degrees Celsius, but the total pressure in your product would now be 11.18 atmospheres. So in the previous case, we held the pressure constant and we lowered the temperature and we have a condensate. In this case, we held the temperature constant, but we are increasing the pressure. That's also another way for you to get a condensate. Okay? And since we have a condensate, your product gas is at equilibrium condition. The partial pressure of water is equal to the vapor pressure of water. Okay? So how do we do this? Since the temperature at your product is 100 degrees Celsius, you can immediately use that in the Antoine equation. Okay? So if we go back to the Antoine equation, your temperature is 100 degrees Celsius. We want to know the partial pressure of water coming from the Antoine equation. We are solving for the pressure. So that's log pressure x is equal to A 8.07131 minus B 1730.63 over C 233.426 plus temperature 100 degrees Celsius. Sorry. Okay, that's 760. So what's next? We now know the vapor pressure of water at 100 degrees Celsius. We also know its partial pressure. It's the same value because we have a condensate. Your product is at equilibrium condition. We can immediately solve for the mole fraction of water. So using Dalton's law, mole fraction of water is partial pressure of water over total pressure. So that is 760. Total pressure is 11.18 times 760 for conversion. What is our... Okay, so 760 cancels, so this becomes 1 over 11.18. 0.0894. That's the mole fraction of water. Now perform the OMB. OMB is F equals W plus P. So we are using the same basis, no? Basis is 100 moles of F. So 100 equals W plus P. When you perform the water balance, we have 0.1 times 100 is equal to W plus 0.0894 times P. Solving the two equations we have. So this is 100 and 1.0894.1 times 100. W is 1.16 moles, and then the product is 98.34 moles. Okay? If we will be comparing the amount of water that was condensed from problem number 3 to the water that was condensed from problem number 2, earlier in the second problem, we determined that the water that was condensed is 3.5 moles. So we can condense 3.5 moles of water if we decrease the temperature. We can condense 1.16 moles of water if we increase the pressure. Technically speaking, it's easier to condense water by decreasing the temperature than by increasing the pressure. No? It's much harder to increase the pressure of a gas than to decrease its temperature. Okay? That is how we integrate our analysis of gas mixtures with one condensable component to our material balance knowledge. Now, every time that you will be encountering air from all of our previous lessons, from reactive and non-reactive processes, you now have to apply the concept of this, no? Air-water mixture, or air plus another condensable component. Okay? Okay. Let's now move on to some of the different ways on how we can express the concentration of gas mixtures. So of course we have the usual mole fraction of water vapor, mole fraction of air, but we have 4 other ways of expressing concentrations. Okay, you have to master all of these 4 concentrations. To begin with, we have to differentiate between the terms humidity and saturation. So technically speaking, they are referring to the same thing, no? But when you hear the word or when you see the word humidity, you always apply it to air-water mixtures. If your condensable component is no longer water, let's say for example you have air and ethanol mixture, you have to use the term saturation. Okay? Those are our terminologies. Whenever you see humidity, you always think of air and water. Whenever you see saturation, you always think that there's no water or water is not the condensable component. Let's begin with the first one. The relative saturation or relative humidity. Again, relative humidity would pertain to water and air. Relative saturation would pertain to air plus something else. Now, this might be familiar to you, no? Relative humidity is something that's used in weather reports or something that's used to report the conditions of a room along with temperature. So the first equation that you see here, that's the equation for relative humidity. We use the variable small h sub r. And the formula is the partial pressure of water over the vapor pressure of water times 100%. Now, the relative saturation is the same equation. It's just that this is no longer water. It's another different condensable component. Okay? Now, if you take a look at this equation for relative humidity, and if you think of our condition for equilibrium, remember, our condition for equilibrium is that the partial pressure of water is equal to the vapor pressure of water. So if this numerator is equal to the denominator at equilibrium, your relative humidity is 100%. Therefore, we say at 100% relative humidity, that is another condition for equilibrium. So we now have 4 conditions for equilibrium when the problem states it, when you are at the dew point temperature or lower, when you have a condensate on the process, and when your relative humidity is 100%. Okay? Let's try to solve this example. What is the partial pressure of water vapor in air on a particular day when the temperature is 28 degrees Celsius with a relative humidity of 60%? So let's list the given. Temperature, 28 degrees Celsius. Relative humidity, 60%. And we are asked for the partial pressure of water vapor. Okay. Again, relative humidity, partial pressure of water over vapor pressure of water times 100%. So how do we do this? You're given the relative humidity, so you can substitute 0.6 equals, you're looking for the partial pressure of water, but we need the value of the vapor pressure of water in the denominator to solve this problem. So what do? We use the Antoine equation. So you see, you're always using the Antoine equation. So practice solving or practice using the Antoine equation. So for the Antoine equation, we're given the temperature and we're looking for the vapor pressure. So vapor pressure of water at 28 degrees Celsius. So let me go back to the Antoine equation. Okay, so that's log of P. So log of X equals A 8.07131 plus B 1730.63 over C 233.426 plus temperature 28. So at 28 degrees Celsius, partial pressure 28.27 millimeters of mercury. Substitute to your relative humidity. We get the partial pressure of water as 28.27 times 0.6. That's 16 points. So that is 17.0 millimeters mercury. Okay? relative humidity is actually very easy to use because it's just the ratio of the partial pressure and the vapor pressure. Okay? That's the first one, and we have 3 to go. Okay, next. Molal saturation or molal humidity. Again, the molal humidity or the first equation refers to air and water mixtures. The second equation, molal saturation, refers to anything other than water as the condensable component. So here's the definition of the equation. On the numerator, you have the number of moles of water vapor. On the denominator, you have the number of moles of dry air. When we say dry air, you subtract the amount of water from the total air because we only want the dry air in the denominator. Okay? That's why in our formula here, your numerator is the moles of water vapor, but remember, we have an equivalency between mole fraction and pressure fraction. That's why you see here that the numerator is the partial pressure of water divided by the total pressure minus the partial pressure of water, because this gives us the number of moles of dry gas, or the denominator here gives us the partial pressure of dry air. Okay? You can also solve the molar humidity in terms of number of moles. So that's moles of water over total number of moles minus moles of water. But in some cases, it's easier to use partial pressures because most often that is what's given. Okay? Let's solve this example. What is the molar humidity of air at a pressure of 768 millimeters mercury with a relative humidity of 78% at a temperature of 28 degrees Celsius? Okay, we're asked for the molar humidity. So here's your given. Again, I will write the formula for the molar humidity. We want the partial pressure of water over the total pressure minus partial pressure of water. If you take a look at the formula, we already have the total pressure. That's your 768 millimeters mercury. What we just need to determine is the partial pressure of water. You're given the relative humidity, which is the partial pressure of water over the vapor pressure of water. You're given the temperature. You know what's coming. You use the Antoine equation. So using the Antoine equation, we can readily solve for the vapor pressure of water at a temperature of 28 degrees Celsius. So we now have our vapor pressure. You can now substitute this to the relative humidity. We can get the partial pressure of water as 28.27 times 0.78. That's 22.05. We can now use this to our molar humidity. That's 22.05 over 768 minus 22.05. And then I will tell you what's the unit of molar humidity. 768 minus 22.05. Okay, that's 0.0296. Okay, let's do 3 significant figures. The unit of molar humidity is, that's moles of H2O per moles of dry air. So whenever you see dA at the denominator, so that is dry air. Okay? Do not forget the units of molar humidity. Moles of water over moles of dry air. Of course, if you are using molar saturation, then that is moles of the vapor over moles of the dry air. Sometimes we also substitute dry air as vapor-free gas, especially if your non-condensable component is no longer air. Okay? Let's proceed. Okay, next, we have the absolute saturation or absolute humidity. Now, this looks similar to molal humidity. No? If you take a look at the formula, we still have the molal humidity. That's the partial pressure of water over total pressure minus partial pressure of water. But we multiply it with the ratio of molecular weight of water over molecular weight of air. That's because the absolute humidity is defined as the mass of water vapor over mass of dry air. So instead of moles, the absolute humidity is just using mass. Okay? You can also say that the absolute humidity is equal to the molal humidity times molecular weight of water over molecular weight of air. So this is 18 over 29. But if you're talking about absolute saturation, that's the mass of the vapor over the mass of vapor-free gas. And do not forget to change the molecular weight ratio. So the numerator should be the molecular weight of the vapor. The denominator should be the molecular weight of the vapor-free gas or the dry gas. Let's try this example. Determine the absolute humidity of compressed air at 27.3 psi with 15% moisture by mole. So you're given the mole fraction of water, 15.7%. So that's 0.157. Okay. We want to determine the absolute humidity. The absolute humidity is defined as the molal humidity, that's partial pressure of water over total minus partial pressure of water, times molecular weight ratio, 18 over 29. Okay? So we're given the total pressure, 27.3 psi. We are given the mole fraction of water. So we can just use Dalton's law to determine the partial pressure of water. So the partial pressure of water is simply the mole fraction of water times the total pressure. 0.157 times 27.3 psi. So no need to convert psi here because it would just cancel. Okay, that's 27.3 times 0.157. 4.2861 psi. Substitute to the molal humidity equation. So 4.2861 divided by total pressure 27.3 minus 4.2861 times 18 over 29. Okay, what's the unit of absolute humidity? 0.116. This is grams water per grams dry air. You can also do kilograms of water over kilograms of dry air, pounds of water per pound of dry air. So whatever unit of mass that you can use, as long as it's the same, because they have to cancel. Okay? We have gone by 3 concentration units. You have relative humidity, absolute humidity, molal humidity. Last one. The percentage saturation or percentage humidity. This might look complicated, but it's simply, on your numerator is your molal humidity, your actual molal humidity, while in your denominator is your molal humidity at the dew point. So you can see that there's just a difference between the partial pressure and the vapor pressure. Okay? So that is the percentage humidity. Let's solve this example. We will be solving for the dew point Relative saturation, molal saturation, absolute saturation, and percentage saturation. You may notice that we are using the term saturation here because if you take a look at the problem, your condensable component is no longer water, it's styrene. The vapor pressure of styrene is 100 millimeters of mercury at 82 degrees Celsius and 200 millimeters of mercury at 100 degrees Celsius. A gas that consists of 10% styrene and 90% dry air is contained in a tank at 100 degrees Celsius and 1000 millimeters of mercury. Okay, let's list the given. At a temperature T1 of 82 degrees Celsius, the vapor pressure of styrene is 100 millimeters mercury. At a temperature T2 of 100 degrees Celsius, vapor pressure of styrene is 200 millimeters of mercury. Your gas consists of mole fraction of styrene, 10%, that's 0.1, and then mole fraction of dry air as 0.9. Your current temperature is 100 degrees Celsius. Current total pressure is 1000 millimeters mercury. Okay, let's start with the dew point. The dew point temperature should be the easiest one to solve here. So how do we solve for the dew point? We go back to the Antoine equation. But if you see here, we don't have the Antoine equation constants for styrene. But what we are given are 2 points. You have T1 PS1 and then T2 PS2. Okay? So remember, at the dew point temperature, this is a condition of equilibrium. The partial pressure of styrene is equal to the vapor pressure of styrene. So what is the partial pressure of styrene? It's simply the mole fraction of styrene multiplied by the total pressure. So that is 0.1 times 1000 mmHg. The partial pressure of styrene is 100 mmHg. Now, since we are at the condition of equilibrium because this is dew point, this is also equal to the vapor pressure of styrene, 100 millimeters mercury. Now, if the vapor pressure of styrene is 100 millimeters mercury, what is its dew point? If you take a look at the given, 100, 100, therefore we say that the dew point temperature is 82 degrees Celsius. Okay? It just so happened that we are already given the temperature and the vapor pressure. But in other cases, if there's no given like this, you have to use the Antoine equation or you have to use the Clausius-Clapeyron equation. Okay? Next. What was the next one? Relative saturation. Relative saturation is S sub R. This is the equivalent of relative humidity. So the definition is the partial pressure of styrene over the vapor pressure of styrene. In this case, what is the partial pressure of styrene? We have already solved for that, 100 millimeters mercury. But the question is, what is the vapor pressure of styrene? If you take a look at our initial conditions, the temperature of your stream is 100 degrees Celsius. Total pressure is 1000 millimeters mercury. So the temperature that we will follow is 100 degrees Celsius and not the dew point temperature. So do not confuse that with the dew point temperature, okay? Your process temperature is still 100 degrees Celsius. So what is the vapor pressure of styrene at 100 degrees Celsius? Again, we are lucky that that's already given. At 100 degrees Celsius, the vapor pressure of styrene is 200 millimeters mercury. Therefore, the percent saturation is 50%. Next, molal saturation. Molal saturation. Okay, so molal saturation is the equivalent of molal humidity. So that is moles of your condensable component or the moles of the vapor over the moles of the vapor-free gas. So we want the partial pressure of styrene over total pressure minus partial pressure of styrene. So the partial pressure of styrene, again, is 100. Total pressure, 1000 minus 100. We get a molal saturation of 100 over 900. Zero 0.111 mole styrene over mole dry air. Do not forget the units. Okay? Next, absolute saturation. Absolute saturation, it's the equivalent of absolute humidity. So this is simply molal saturation multiplied by the molecular weight ratio. So at the top, molecular weight of styrene. So styrene is C8H8. Let's compute 12 times 8 plus 8. 104 over, at the bottom is the molecular weight of dry air, that's 29. So we get an absolute humidity of 104 over 29 times 0.111. That's 0.398 grams styrene per gram of dry air. Last one, percentage saturation. Let's use the more proper variable, S sub P. For the numerator of the percentage saturation, we have the molal saturation, S sub M, which the value is 0.111. Your denominator would be the molal humidity if your operating temperature is the dew point temperature. So going back, our operating temperature is 100 degrees Celsius for this problem. We are going to assume that this is the dew point temperature for the sake of the percentage humidity. Okay, so at 100 degrees Celsius, the vapor pressure is 200 millimeters mercury. So we are going to use that. Your actual molal saturation is 0.111 divided by, for the molal humidity at saturation, or for the molal humidity at the dew point, that would be 200 over 1000 minus 200. Of course, times 100%. So that is 0.111 over 200 over 800. 1000 minus 200. 44.4%. That is our percentage saturation. Okay? Do not confuse yourselves between saturation and humidity. They are just different terms pertaining to the same equations. Okay, so this next one is very similar to our previous example, no? So this is number 1 in your worksheet number 8. Okay, next. Okay, so I will be answering the first problem, and then the second problem here, a room contains 12,000 cubic feet of air, etc. That's the number 2 of your worksheet number 8. So let's answer the first one. Oxalic acid is burned at atmospheric pressure with 248% excess air, so that the 65% of carbon turns into CO2, the rest forming CO. Calculate the dew point of the flue gas. So this is now a combination between combustion problems and material balance involving gaseous mixtures with one condensable component. So let's draw the given. Okay, so obviously this is largely a combustion problem, so I will be drawing it like a combustion problem. We have a burner. Your fuel to the burner is the oxalic acid, H2C2O4. You have the air supplied at 248% excess. So 65% of the carbon becomes CO2. So that tells me that our flue gas contains both CO2 and CO. It should also contain water because we have hydrogen in the feed, and it should also contain the excess oxygen and nitrogen. So we have oxygen and nitrogen in the air. So let's label the unknowns. Okay. So we are required to determine the dew point of the flue gas. Now, if you take a look at your flue gas, you only have one condensable component in there, and that is water. So let me highlight water. All of the rest you consider as non-condensable. For these types of problems, you just need to know the mole fraction of water in your flue gas stream, then you're good. You can already determine the dew point temperature. Okay? So it's burned at atmospheric pressure. So we say that the total pressure is 1 atmosphere. The first approach to this is you solve this as a regular combustion problem. Basis, 100 moles of oxalic acid. Okay? Next, NO2 Theo. We assume that all of the oxalic acid is combusted completely without regard to how much CO2 or CO is formed. So our combustion reaction is H2C2O4 plus O2 yields CO2 plus H2O. We just need to balance this equation. How do we balance this? We multiply this by 2. This becomes 2 and this becomes 4. So hydrogen is 4, carbon is 4, oxygen is 8, 9, 10. This is 8, 9, 10. Okay, that is balanced. So going back to our NO2 Theo, based from the balanced equation, for every 2 moles of oxalic acid, we use 1 mole of oxygen. So our NO2 Theo is 100 divided by 2, that's 50 mole O2 Theo. We use the percent excess, so 248% is 2.48. That is fed minus Theo over Theo. We now know N1. This is the reason why you don't forget your previous learnings, because we just keep on using and using them with new learnings. Okay? Plus 50. So 174 moles oxygen. That's our N1. We multiply this by 79 over 21. We get N2 and N7. So this is just a routinary combustion solution. We have 654.57 moles nitrogen. Okay, so we're done with N1, N2, N7. Next, we can now perform the carbon balance. What's your carbon balance? That is 2 times the feed is equal to N3 plus N4, but 65% of the carbon forms, am I right? Okay, 65% of the carbon, so that is 0.65 of 2 times 100 forms CO2, and the remaining 35% forms CO. We can already solve for N3 here. 100 times 2 times 0.65, 130 moles CO2. And then substitute this to your carbon balance. You can solve for N4. That is 200 minus 130. That is 70 moles CO. Done? Done. Next, hydrogen balance. So what is our hydrogen balance? That is 2 times the feed is equal to 2 times N5. N5 is 100 mole H2O, right? Your only sources of hydrogen are in oxalic acid in the feed and water in the product. So we're done with N5. Last one, N6, we perform the oxygen balance. That is 4 times the feed plus 2 times N1 is equal to 2 times N3 plus N4 plus N5 plus 2 N6. We can solve for N6. So that is 400 plus 2 times 174 minus 2 times 130 minus 70 minus 100 divided by 2. 159 mole O2. So we're done with N6. Now for the fun part, we need to solve for the dew point temperature. So let me just determine the total number of dry flue gas. If you will remember, we had the ORSAT analysis, right? For the ORSAT analysis, we are only considering the dry flue gas. So that is everything except water. So that's the same here. The dry flue gas is equal to N3 plus N4 plus N6 plus N7. Everything in the flue gas except water. So that is CO2 130, CO 70, O2 159, N2 654.57. That is 1013.57 mole dry flue gas. And how much mole is your water? 100 moles of water. So let me erase this part. We will solve for the dew point temperature here. Okay, what is the mole fraction of water in the flue gas? That is 100 moles of water over the dry flue gas is 1013.57 plus 100. The mole fraction of oxygen in the flue gas, that's 100 over 100 plus 1013.57, 0.0898. Next, how do we get the dew point temperature? We use the Antoine equation, but for the Antoine equation, we need the partial pressure, okay? So the partial pressure of water in this case would simply be the mole fraction of water times the total pressure, which is 0.0898 times 1 atmosphere. So I'm going to multiply this by 760 millimeters mercury so that it would already be in mmHg. That is 68.25 mmHg. This is also, since we are solving for the dew point temperature, that's a condition of equilibrium. So this is also the vapor pressure of water at the dew point. So we revisit the Antoine equation. This would get repetitive to you, no? And then we can get the dew point temperature. So let's see the constants. Okay, so that is log 68.25 is equal to A 8.07131 8.07131 minus B 1730.63 over C 233.426 plus temperature. That is your unknown. That's the dew point temperature. Shift solve. The dew point temperature of the flue gas is 44.0 degrees Celsius. So let's just 44 degrees Celsius. So that is how you integrate computations for gaseous mixtures to other aspects of material balances. Okay, so for your exam number 3, expect that everything would be mashed together. Reactive processes, non-reactive processes, together with gas mixtures with one condensable component. Okay, review everything, or better yet, just don't forget anything. Okay, let's proceed. Again, this is your item number 1 for worksheet 8. The second item here, a room contains 12,000 cubic feet, etc. That's your problem number 2. I will be solving the first one here, no? So the second is your problem number 3, and then this is your problem number 4. So you have 4 items in your worksheet number 8 total. The due date for worksheet number 8 is right before we start the exam in Saturday, or depending on the result of the survey. Okay, let's solve the first one. In a device used to produce potable water, humid air at 90 degrees Fahrenheit, 29.7 inches mercury, and 95% relative humidity is cooled to 45 degrees Fahrenheit at constant pressure. What volumetric flow rate of air into the cooler is required to provide 10 gallons per minute of condensed water? So let me draw the given. Okay, here we have the given. So our unit here is a cooler, no? And in this cooler, it was explicitly stated that you have a condensate. In fact, you are collecting the condensate. Okay? Our condensate is 10 gallons per minute, and we want to find out how much flow rate of wet air into the feed do we need for us to produce 10 gallons per minute of fresh condensed water. Okay, right out of the bat, you know that this is a cooler and you know that you have a condensate because it was explicitly stated. So therefore, you have to note it immediately that P is your equilibrium condition. So in your product, you say that the partial pressure of water is equal to the vapor pressure of water, so that you don't forget. Okay? Now, before we start solving, another thing. Remember the definition of relative humidity? That's the partial pressure of water over the vapor pressure of water. And since those are equal in the product, therefore, your relative humidity in the product is equal to 100%. So these are the information that are not explicitly stated, but you are expected to come up with these conditions. Okay? So these are our equilibrium conditions. So the required flow rate of F. And since our required and all of our given are in English units, I will no longer be converting them to SI units. But if you are more comfortable working with SI units, then you have to convert everything to SI, and in your final answer, you convert back to English. Okay? Cubic feet per minute. Am I right? Okay. Let's first approach this like a regular material balance problem. Okay? So you know that in your feed, you have water vapor, you have dry air. Your W is pure water in the liquid phase, and your product is water vapor and air. Okay? So let's first set our basis. You're given a flow rate, so the basis is 1 minute operation. That gives us a value of W as 10 gallons. Now, we cannot use gallons in our material balance because it's in volume. So let me turn it into mass and moles. So the 10 gallons of liquid water, we can actually use its density. So let me first find the density of water in pounds per gallon. Okay, let's use 8.344 pounds per gallon. 8.344 pounds mass per gallon. So we have a value of the pounds of water required. Times 10. So that's 83.44 pounds of liquid water. Now, in some instances, you might also want to have this value of the water in terms of moles. So if ever we will be needing it in moles, we will just be converting it later. Okay? Now, let's perform the OMB. What is your OMB here? F is equal to W plus P. F is equal to 83.44 plus P. Now, keep in mind that this is not a reactive process. So our OMB can either be an overall mass balance or an overall mole balance. Remember, you cannot use moles in an OMB for reactive processes, but for non-reactive processes such as this, you can use moles in OMB as well as mass. Okay? After OMB, let's proceed with the water balance. Okay, but before we can proceed with the water balance, we first need to know the composition of your feed and of your product. Okay, let's start at the feed. So what do we know about the feed? We know that the feed has a given relative humidity of 95%. So a 95% relative humidity means that we can determine its partial pressure. So the partial pressure of water over the vapor pressure of water. The vapor pressure of water can be determined from the Antoine equation since we are given the temperature of the feed, that is 90 degrees Fahrenheit. The Antoine equation given to us is in terms of SI units, that is in millimeters mercury and degrees Celsius, but there are actually online calculators for the vapor pressure of water that you can also use. So let's search for a calculator. But in the absence of a calculator, or if you are in situations wherein you cannot browse the internet, let's say for example for other exams, you have to use the Antoine equation. Okay, so I will be writing it here using the Antoine equation. The vapor pressure of water at 90 degrees Fahrenheit is equal to 36.02 millimeters of mercury, which we can later convert to inches of mercury or vice versa. Okay? So now that we have that, we can go back to the definition of the relative humidity and solve for the partial pressure of water, which is 0.95 times 36.02. 36.02 times 0.95. That is 34.219 millimeters mercury. Okay, now how do we use this partial pressure values to determine the mole fraction of water? Well, you go back to Dalton's law of partial pressures. The mole fraction of water, remember we are still in the feed, no? The mole fraction of water is simply the partial pressure of water, 34.219 millimeters mercury, divided by the total pressure. Total pressure is 29.7 inches mercury. Now, we just need to convert from inches to millimeters. So 1 inch of mercury is 25.4 millimeters mercury. We now get the mole fraction of water. So this is 34.219 over 29.7 times 25.4. 0.0454. And if you want to get the mole fraction of air, you simply subtract that from 1. 0.9546. Okay, so these are the mole fractions of water and air in the feed. Okay, so this is just our mini calculations. I can now erase this. So let me first write mole fraction of water here is 0.0454. Next, let us now consider the product side. And we do the same process. On the product side, your given is the temperature is 45 degrees Fahrenheit. So it's lower because it just passed a cooler. And then we know that we have here the equilibrium condition because we have a condensate. Therefore, our relative humidity is 100%. So let us use the Antoine equation again. So we are at the product. Let's use the Antoine equation to determine the vapor pressure of water. This is at 45 degrees Fahrenheit. The vapor pressure is 7.58 millimeters mercury. Okay, now the mole fraction of water in the product is equal to the vapor pressure, which is equal to the partial pressure, 7.58 millimeters mercury, divided by the total pressure. This is an isobaric process, meaning constant pressure, so it's still 29.7 inches of mercury. We have a mole fraction of 7.58 over 29.7 times 25.4. 0.0100. Okay. If you want to have this at 4 decimal places, it's okay. Okay? So we now have the mole fraction of water in the product side as 0.01. Now we can perform, or now we can continue our material balances. So the material balance would just carry out as usual. We now have our equation number 1 coming from the OMB. So let's just perform the water balance. But before that, let's convert the mass of water to moles, because it's easier to perform the balance in moles, no? Because we are given mole fractions. So we have 83.44 pounds mass of water, and then 18 pounds mass is to 1 pound mole. Okay, we have 4.64 pound mole H2O. This is your W. Okay, going back to the OMB, that is feed is equal to 4.64 plus P. The only difference is that this second OMB is now in moles, okay, for simplicity. Next, water balance, we have 0.0454 F plus equals 4.64 plus 0.01 P. We now have two equations, two unknowns. We can solve for the feed and the product. That is 1, negative 1, and then 4.64. Second equation, 0.0454, 0.01, negative 0.01, and then 4.64. 4.64. Our feed, this is in moles, 129.76 pound moles. Product, 125.12 pound moles. And since our basis is 1 minute, so this becomes pound moles per minute. And we are required to determine the volumetric flow rate of the feed. So we resort to the ideal gas equation. PV equals nRT. V is equal to nRT over P. And then you do the rest. We already determined the number of moles of the feed. You simply substitute that to the ideal gas equation to determine its volume. And since the basis is 1 minute, that becomes automatic volumetric flow rate. Okay, just remember to use a value of R with consistent units or with English units. Okay, that's it. This is how you include the analysis for gaseous mixtures with one condensable component into our usual material balances. Okay, so again, I repeat, this is number 1. The second item here is number 2. The second item here is number 3. And this is number 4. In this last problem, I have given you the Antoine constants for benzene. Okay? So that's it for this lesson. This is our final lesson. I hope that you all pass this course so that you will no longer have to repeat this. Okay? I hope you've learned something, and as always, keep safe.